Let's find a probability distribution for a probability experiment. We have a four-sided die that is weighted on one side, so it's not a fair die. Even though there's four sides and four different options or outcomes possible, they don't share the probability uniformly. In fact, this is how it's broken up. The probability of rolling 4 is 3 times greater than any other number. So that seems important. We're going to use that. So we know that the whole sample space omega, that was too big. The whole sample space consists of, it's a four-sided die, so you can get a 1, a 2, a 3, or a 4. So I know that one of these things has to happen. So the probability of a 1 plus the probability of 2 plus the probability of rolling a 3 plus the probability of rolling a 4, even though I don't know what those are at this point, I know that they have to sum to be 1, right? Because that's my entire sample space. One of these things has to happen. And let's keep going. However much the probability of 1 is, I don't know it. From the problem statement, it's the same as the probability of 2, right? It's only weighted on one side. The 4 is the only one that's different. So the probability of 1 is something. The probability of 2 is also something. The probability of 3 is also that same thing. But the probability of 4, how does that relate? The probability of rolling a 4 is 3 times all of the other numbers. So we have 3 dots here. Okay, so 1 dot plus 1 dot plus 1 dot plus 3 dots has to be equal to 1. How many dots do we have? 1, 2, 3, 4, 5, 6. So 6 dots has to be 1. So each dot takes up 1/6 of the space, and 4 gets 3 of those dots. So our probability distribution, let's give it as a table and as a histogram. So what are the events possible? We've already discussed them. When you roll a dice once, you're going to get a 1, a 2, a 3, or a 4. And then what are the probabilities? We just did all that work. A 1 is 1/6 of the area. A 2 was the same. The 3 was the same, 1/6. And it was the 4 that was 3 times as likely. Right, that got 3 1/6. And a good way to double check yourself is that this should sum to be 1. If you add up the probabilities of all of your possible events, you should get 1. And in fact, 1 plus 2, or sorry, 1, 2, 3, 4, 5, 6 does give you 6/6 or 1. So you didn't lose any probabilities. It's always a good idea to check yourself that you did that correctly. If we view this probability distribution as a histogram, which is very helpful, the heights will be our probabilities. Our events are given to us on the x-axis, 1, 2, 3, or 4. And the 1, the 2, and the 3 all get the same probability of 1/6. The 4 is 3 times higher than that at 3/6 or 1/2, right? And the area underneath this distribution should be equal to 100% or 1.